Back in 2015, the CEO of Turing Pharmaceuticals, Martin Shkreli, raised the price of Daraprim from $13.50 per pill to a whopping $750 per pill. This is an increase of over 5,000% overnight. During the period of 2015 to 2017, NurdRage attempted to make pyrimethamine. Although along the way there were many failures and mishaps, in September 2017, he successfully made pyrimethamine from OTC chemicals. However, NurdRage made his pyrimethamine videos as a series and not a compilation. This video is a compilation of all NurdRage's videos on the synthesis of pyrimethamine. First, I'll briefly go over the reaction scheme. The first reaction would be making chlorine gas and cyanuric acid. This is done by reacting hydrochloric acid and trichloroisocyanuric acid. The chlorine gas is then used to chlorinate toluene by the use of a ferric chloride catalyst. This produces two isomers of chlorotoluene, para-Chlorotoluene and ortho-Chlorotoluene. These chlorotoluene isomers are then separated by sulfonation and steam distillation. Once the para-Chlorotoluene is isolated, the next step is the preparation of sodium cyanide using cyanuric acid, sodium hydroxide, and activated carbon. We will not be including this due to YouTube terms of service. After sodium cyanide is prepared, then the para-Chlorotoluene is then subjected to free radical chlorination using a 50-watt 400 nanometer UV LED chip. This will produce para-Chlorobenzyl chloride, which is then reacted with potassium iodide and acetone. This will produce para-Chlorobenzyl iodide and a precipitate of potassium chloride. This reaction is also known as the Finkelstein reaction. The para-Chlorobenzyl iodide then reacts with sodium cyanide to produce para-Chlorophenil acetonitrile. Here on the left, you can see that Chloroform and sodium propionate is prepared by reacting methyl ethyl ketone with sodium hypochlorite. This reaction is also known as the haloform reaction. The sodium propionate is then converted to propionic acid by reacting it with sulfuric acid. The propionic acid is then reacted with ethanol to make ethyl propionate in a reaction called the Fischer esterification. In the next step, chloroform is reacted with a hot solution of sodium methoxide and methanol to produce trimethyl orthoformate. The sodium methoxide was made by reacting sodium metal with methanol. The sodium required was made in another video by the alcohol catalyzed magnesium reduction. Next, the ethyl propionate and the para-Chlorophenil acetonitrile is then used to make 2-para-chlorophenyl 3-oxopentane nitrile by refluxing these reagents in the presence of sodium methoxide and dioxane as a solvent. The oxopentane nitrile is then reacted with trimethyl orthoformate under reflux in methanol using sulfuric acid as a catalyst to produce 2-para-chlorophenyl 3-methoxypentane nitrile. Guanidine carbonate is then reacted with hydrochloric acid to produce guanidinium chloride, which is then reacted with sodium methoxide to produce free-base guanidine and methanol. Finally, after all of this work, we finally get to the last step in making pyrimethamine. The final step in making pyrimethamine is by reacting the methoxypentane nitrile with free-base guanidine to produce the final product, pyrimethamine. I hope this made your understanding of the series easier. Anyhow, I hope you do enjoy the video, and please be sure to check out NurdRage's channel if you've not done so already. NurdRage has kindly given me the permission to compile his series and upload the compilation to my channel. Huge thanks to NurdRage if you're watching this video. Without further ado, let's get into the video.
I need some toluene for my lab, and in the past I was able to buy it directly as paint thinner, but now I can't find a pure source, and all I could get was this lacquer thinner that claims to contain toluene mixed with methanol and methyl ketone. Since I have no other choice, I'm going to try and fractionally distill out the toluene. So here's our fractional distillation setup. Okay, let's turn the stirring, the heating, and the cooling water. Now when doing a distillation, it helps to thoroughly research your components and the azeotropes and list them out in a table in order of temperature. We can see that the acetone and acetone methanol azeotrope boil at around 56 to 55 degrees Celsius, while the next cluster of compounds boils around 64 degrees Celsius. So if we're condensing near 55 degrees, then we know we have acetone as azeotropes. But if we go past that into the 64 degree range before we condense, then we know we have no acetone. Looks like we're getting a nice fraction of methanol azeotropes. Okay, looks like we're rising again and going past the methanol azeotropes. At this point, we might be condensing methyl ketone. I'm going to change out the receiver and collect this new fraction. Yeah, looks like we're moving past the boiling point of methyl ketone, which should be around 79 degrees Celsius. Perhaps I'm heating too much and overloading the column with vapor. I'm going to turn down the heat just a bit to slow down the distillation. Well, that sucks. Now it's going too slow and not reaching the top of the column at all. And yet I only dialed back the heat a small amount. I'm going to turn up the heat and just boil out this low boiling component even if I lose a bit of toluene. Okay, looks like we finally reached the boiling point of toluene and have boiled out all of the lower boiling components. The temperature seems stable, so this toluene should be pure. Let me change out the receiver, and now we're collecting pure toluene. And we are done. The source flask just has some impurities, so we're going to turn off the heat and let it all cool. And here's our collection of fractions. Fraction 1 is what I believe is the azeotropes of methanol. Fraction 2 is the mixture of methyl ketone and toluene that came from the overloaded column. And fraction 3 is our pure toluene. Here we are with just fraction 2 being distilled, and the column has been wrapped in aluminum foil. And there we go. Looks like we've reached the temperature for toluene. Let me change the receiver again. And we are done, and here are our fractions. 2a is the stuff that came off at 82 degrees Celsius, whatever that is. Fraction 2b is the overlap of 2a and toluene, which is very little. And 2c is our extra toluene. This is the first step to making the antiprotozoal drug pyrimethamine. First, we get a liter-sized flask and add some fine steel wool. I'm using a 10-gram roll, but the exact quantity is not critical. Now we add 500 milliliters of toluene. Anyway, here's our mixture, and around it we set up this chlorine generator. So let's get started. First, we drip in the hydrochloric acid, and we can see the yellow chlorine gas forming. I'm using enough reagents to produce 4 moles of chlorine atoms, or 2 moles of diatomic chlorine gas. It'll take a minute or so for the air to purge out the tubes before the chlorine gets to the toluene. And there we go. What's happening is the chlorine is first reacting with the iron in the steel wool to produce ferric chloride. This ferric chloride then acts as a catalyst for the reaction of chlorine with toluene to produce chlorotoluenes and hydrogen chloride. This is the textbook reaction of electrophilic halogenation taught in almost every university or college organic chemistry course. Now, if you happen to have anhydrous ferric chloride, you can add that directly as a catalyst. Okay, all the chlorine has been added. Now we just let the mixture stir for an hour to complete the reaction, and then we let it cool completely to room temperature. Here we are after everything is at room temperature. Now we add 500 milliliters of water to dissolve the iron chlorides, any soluble impurities, as well as wash out any residual hydrogen chloride. Well, I forgot to remove the unreacted steel wool. You can use an iron wire hook to fish it out. Okay, back to the mixture. We add the rest of the water and give it a thorough stir to wash the chlorotoluenes. Turn off the stirring and let the layers separate. Now we remove the lower aqueous layer. Here we are after most of the aqueous layer has been removed. At this point, we now add a saturated solution of sodium bicarbonate. The amount you should add should bring the total solution volume to 1 liter again. What we're doing here is using the alkaline sodium bicarbonate to react away any remaining hydrogen chloride. Now once again we remove the aqueous layer by siphoning. And here we are, our washed mixture of crude chlorotoluenes, byproducts, and unreacted toluene. To separate it, we're going to use our least favorite technique, fractional distillation. What distills off first is going to be a tiny amount of residual water from the washings and toluene. Then pure toluene will distill over at 110 Celsius. Continue distilling until the temperature rises to 135 Celsius. Then switch out the receiver and you'll then be distilling the chlorotoluenes. Chlorotoluenes themselves distill around 160 Celsius. Continue distilling until nothing distills over, or if you reach a temperature of 170 Celsius. And there you have it, chlorotoluene. Now the chlorination of toluene actually forms different isomers of chlorotoluene, all with very similar properties. Orthochlorotoluene, metachlorotoluene, and parachlorotoluene. Now, in electrophilic halogenation, the methyl group actually affects the electron distribution of the aromatic ring, and metachlorotoluene product is negated. The major products are ortho and parachlorotoluene. To make pyrimethamine, we want parachlorotoluene. For now, we can still use this mixture of ortho and parachlorotoluene isomers by adding a second separation step to isolate just the parachlorotoluene. So here is our mixture of chlorotoluene isomers, about 450 grams worth. Now add about 65 milliliters of concentrated sulfuric acid. This corresponds to a 1/3 molar equivalent. Now set up a Dean Stark apparatus around the flask operating in heavy return mode. Now turn on the heating to 300 degrees Celsius and let boil. What we're doing is sulfonating the chlorotoluene and releasing water. By turning up the heat high enough to boil the mixture, the water boils out along with chlorotoluene. The Dean Stark trap allows us to conveniently separate and return the chlorotoluene and just keep the water. By removing the water from the reaction, we drive it forward. Now an interesting thing happens with the isomers of chlorotoluene. Orthochlorotoluene reacts faster and is more stable than parachlorotoluene. This is because the sulfonate group is quite bulky and thus is more stable on positions far away from any other substituent. On orthochlorotoluene, this is easy since there are 2 positions it can react with that aren't beside another substituent. But on parachlorotoluene, wherever it goes, it will bump against another substituent. So parachlorotoluene sulfonation is less favored than orthochlorotoluene. This effect of physical crowding affecting reactivity is called the steric effect. Now you're probably wondering, if I know this mixture is 60% orthochlorotoluenes, which I want to remove, why did I only add 1/3 equivalent of sulfuric acid, which is not enough to remove it all? Well, I did try adding a stoichiometric scientific equivalent, but I then noticed a large amount of decomposition happening. The Chlorotoluene sulfonic acid decomposed at high temperatures and concentrations to chlorocrystals and sulfur dioxide. By limiting the sulfuric acid to less than 1/3, we limit the concentration of Chlorotoluene sulfonic acids and thus limit the decomposition. Okay, looks like we're done. So here we are. Now, while some of our chlorotoluenes is in the Dean-Stark trap, most of it is here as a mixture of chlorotoluenes, chlorotoluene sulfonic acid, and decomposition products. To the mixture, add an equal amount of water. Stir it up until thoroughly mixed. Now assemble the Dean-Stark apparatus around it and set it up for light return mode. Now simply heat up the mixture until boiling and start collecting the heavier components. Now you might be wondering, if we originally made the chlorotoluene sulfonate by sulfonation and removing water, wouldn't adding the water back in hydrolyze it and thus reverse the process, completely destroying our progress? You're absolutely right, and this would happen at higher temperatures. But since we add so much water, the mixture is boiling and thus maintaining a lower temperature at about the boiling point of water. At this lower temperature, we can take advantage of azeotropic distillation without worrying about the reverse reaction. Here is our chlorotoluenes, and I've decanted most of the water. This mixture is enriched in para-chlorotoluene isomers and depleted in orthochlorotoluenes. The residue back here contains our orthochlorotoluene sulfonate and some water. Now this mixture has an unknown ratio of para and orthochlorotoluenes. We know it's been para-chlorotoluene enriched, we just don't know if it's pure. Fortunately, there is a simple test we can perform. Orthochlorotoluene has a much lower freezing point than para-chlorotoluene, so we can roughly figure out our purity based on that. Take a small sample of your chlorotoluene mixture and put it in the freezer. If it doesn't freeze at all, then it has too much orthochlorotoluene. If it freezes, then make a mixture of ice water and place the sample vial in that. If it melts again, then it's richer in para-chlorotoluene but not quite pure enough. If it stays frozen, then it's highly pure para-chlorotoluene. Anyway, in our first run back here, the melting point should have remained liquid even in the freezer. So we still have a lot of orthochlorotoluene that we need to separate. We'll need to do our sulfonation again. Make a note of how much chlorotoluene you have now and calculate how much sulfuric acid you'll need to equal 1/3 molar equivalent. Anyway, here is the purified para-chlorotoluene. To be absolutely sure, I sent off a sample for NMR analysis. As you can see, the clean spectrum shows we have indeed produced pure para-chlorotoluene. Now for storage, I recommend adding some molecular sieves to remove the cloudiness that comes from suspended water droplets. As for the orthochlorotoluene sulfonates, we can now convert back to orthochlorotoluene. The process is actually quite simple. Just gradually heat the mixture and distill off the water and orthochlorotoluene. As the temperature rises, the water remaining reacts with the orthochlorotoluene sulfonates to produce sulfuric acid and orthochlorotoluene. The orthochlorotoluene boils off and distills over. Unfortunately, there's also a large amount of decomposition at these temperatures to chlorocrystals and sulfur dioxide, so our yield is severely affected. Anyway, after many aggravating hours of work, I finally got some orthochlorotoluene. NMR analysis shows I have reasonably pure orthochlorotoluene. That is how you use steric effects and sulfonation to separate ortho and para-chlorotoluene isomers. This is another step in our synthesis to the antiprotozoal drug pyrimethamine. We're going to make p-Chlorobenzyl chloride, also known as 4-chlorobenzyl chloride. First, we have our sample of para-chlorotoluene in the Erlenmeyer flask. We're going to boil that until it refluxes. Now, over here is our chlorine generator and drying flask. This generator is loaded with enough chemicals to produce 1 mole equivalent to p-Chlorotoluene of diatomic chlorine gas. Now after the gas is dried by the sulfuric acid, it passes up here and down this condenser column to the Claisen adapter. There it will meet the para-chlorotoluene vapor that's boiling up from the Erlenmeyer flask. Once the two gases are mixed, the fun part happens over here when it passes over the ultraviolet light emitting diode chip, or UV LED chip. The wavelength is about 400 nanometers. Now the UV light initiates the reaction between the gases, and the heavier products will condense in this exit column and drip back down into the boiling flask. The lighter byproducts will not condense and exit out the top. Anyway, turn on the heating, the cooling water, and wait until the p-Chlorotoluene starts to reflux. Now turn on the UV light and start generating the chlorine admitting it to the reaction. What's happening is the ultraviolet light is initiating free radical chlorination. The light breaks up the chlorine into chlorine radicals. These chlorine radicals attack the methyl group on the p-Chlorotoluene to form p-Chlorobenzyl chloride as well as hydrogen chloride. The hydrogen chloride gas escapes out the top of the column, but the high boiling p-Chlorobenzyl chloride condenses and drips down into the flask. Since it has a higher boiling point than p-Chlorotoluene, it should stay in the flask and never get chlorinated. Now what's interesting about this reaction is that it only chlorinates the methyl group, not the ring. In contrast, when we were making chlorotoluenes, we also used chlorine gas, but by using an iron chloride catalyst rather than UV light, we chlorinated just the ring. This demonstrates the importance of selecting the right reaction conditions to influence the mechanism you want. Now you'll notice the Claisen adapter being filled with black soot. This is because we're having small chlorine fires, and you can see them as tiny little orange flashes. That orange streak is a chlorine fire. I'm adding too much chlorine too fast, and that's creating a mixture rich enough to burn. Now all the oxygen has been purged out by the continual reaction, but chlorine itself is a powerful oxidizer, and thus it can support combustion in some instances. Now for our product, we don't want this to happen, so we'll need to stop it. The process is similar to stopping combustion with regular fire. We just slow down the rate of chlorine addition to create a mixture too rich in fuel to burn. Here we go. Looks like the burning chlorine has been reduced. And here we are, the reaction is finished and allowed to cool. The flask should now contain p-Chlorobenzyl chloride as well as unreacted p-Chlorotoluene, as well as any decomposition products from the burning we saw earlier. Now rearrange the apparatus and set up for fractional distillation. Our target p-Benzyl chloride has a boiling point between 216 and 222 Celsius, so discard everything below 200 degrees Celsius. Then start collecting the fractions between 200 and 230 Celsius. And there we have it. P-Chlorobenzyl chloride. Here is the NMR spectrum proving we have a relatively pure product. My yield was 50 grams or about 65%. We are now entering step 4 of making pyrimethamine, and to do that we need to make p-Chlorophenyl acetonitrile. First we get 50 grams of p-Chlorobenzyl chloride. Now to this we add 7.2 grams of potassium iodide. Now we add 19.3 grams of sodium cyanide. Then we add 250 milliliters of acetone that has been dried overnight with molecular sieves. Remember to add in a stir bar. Now on top of the flask, set up a reflux condenser column. Vigorously stir the mixture and gently raise the temperature until it just starts to reflux. Two things are happening. First, the potassium iodide is reacting with the p-Chlorobenzyl chloride to form p-Chlorobenzyl iodide and potassium chloride. Now this might seem odd since organochlorides are more stable than organoiodides, but this reaction works because it's being driven forward by the very low solubility of potassium chloride in acetone. Potassium iodide is slightly soluble, so the reaction proceeds forward. This is a useful trick in chemistry to make organochlorides into more reactive organoiodides. It's such a useful reaction that it even has its own name, the Finkelstein reaction. Usually it's done with sodium iodide since that works even better than potassium iodide. I'm using potassium iodide because I ran out of sodium iodide. Now if you're wondering, the aromatic perichlorine does not react because aromatic halides are not susceptible to SN2 nucleophilic substitutions. Okay, after that occurs, the sodium cyanide now reacts with the newly formed p-Chlorobenzyl iodide to make p-Chlorobenzyl cyanide, also known as p-Chlorophenyl acetonitrile. The sodium iodide that was produced then goes back into the original step to create more p-Chlorobenzyl iodide. Now unfortunately this overall reaction is very slow since it relies on salts with only weak solubility in acetone. Even under refluxing, this will take a full 24 hours or so. And here we are after 24 hours and then letting it cool. Now we have to isolate our product. First we filter over this fretted funnel. To maximize recovery, we also wash the salts with acetone. Now p-Chlorophenyl acetonitrile is clear, but our filtrate is orange from the impurities. Anyway, set the filtrate aside and move the fitted funnel to a new collection flask. We now dissolve the residue in water. These salts contain unreacted cyanide and we should deal with that first. Once it's all dissolved, we add oxidant like bleach or hydrogen peroxide. I'm using sodium dichloroisocyanurate, which is a highly soluble form of pool chlorine. The idea is to convert the cyanide into relatively harmless cyanate. Once again, make sure you're doing this in a fume hood. Now back to our acetone filtrate. Set up a simple distillation apparatus and distill off the volatile acetone from our reaction mixture. Set the hot plate temperature to 130 Celsius. The p-Chlorophenyl acetonitrile boils well above that, so we don't have to worry about distilling over. While I can easily crank the temperature higher, I instead want to be as gentle as possible so we don't burn and decompose our product. Keep distilling until the temperature starts dropping, indicating everything that can boil at 130 degrees Celsius has boiled off. And here is our residue containing our product, as well as all the side products and contaminants. Now we need to wash out any water-soluble contaminants. Add in 150 milliliters of water and stir. Now the brown color is from small amounts of triiodide resulting from the oxidation of iodide ions with air. To reduce them, we add in 15 grams of sodium metabisulfite. This dissolves in the water and reduces the triiodide ions into clear iodide ions. This will help us wash them out. Stir the mixture for about half an hour. Okay, now using a separatory funnel, recover the lower organic phase and discard the upper aqueous phase. P-Chlorophenyl is denser than water, so that's why the phase sinks rather than floats, as in most organic extractions. And there is our crude P-Chlorophenyl. For better purity, I recommend you wash the organic phase again with 100 milliliters of distilled water. To increase our purity further, we cool the mixture in the refrigerator to 5 Celsius and let it crystallize. P-Chlorophenyl has a melting point of about room temperature, so we can purify it that way. Just pour off what doesn't solidify. And there we have it, 44 grams of crude product. To get even higher purity, we first remelt the product in hot water, and then we set aside the crude liquid P-Chlorophenyl in a room at 18 degrees Celsius and let it sit. A precision temperature controlled cooler is best if you have one. It will very slowly crystallize. Unlike the tiny crystals from putting it in a refrigerator, these very large crystals are much better at excluding impurities. Wait a few days or even weeks until the crystals no longer grow, and then pour off the liquid. This should be exceptionally pure P-Chlorophenyl. The yield is very low though, about 6 grams or 12%. And this beautifully clean spectrum proves we do have our target P-Chlorophenyl. So we have successfully made high purity P-Chlorophenyl. Our crystallized yield was only 12% though, so let's see if the uncrystallized supernatant is still good to use. And this is the NMR spectrum of the supernatant liquid. It's actually pretty good for an amateur level synthesis. A significant impurity is this stuff. This is P-Chlorobenzyl. It's actually a side product of our reaction. We made P-Chlorophenyl by nucleophilic substitution of cyanide onto a benzylic halide. But cyanide is nucleophilic on both ends. Both the carbon and the nitrogen are nucleophilic, and either side can attack the substrate. Now the carbon side is more reactive in water-free conditions, which is why we used acetone with the water removed. But attack by nitrogen is not eliminated. What we get as a minority product is P-Chlorobenzyl isocyanide. This stuff is actually quite reactive, and when we stir it with water, we hydrolyze it to form P-Chlorobenzyl and formic acid. The formic acid is soluble in water and was washed out during our washing steps. So what we have left is this P-Chlorobenzyl impurity that now appears in our spectrum. We can actually remove this stuff by washing again with some dilute hydrochloric acid. This reacts with the amines and converts them to water-soluble salts. Anyway, we have successfully made P-Chlorophenyl, also known as P-Chlorobenzyl. Step 4 in our synthesis of pyrimethamine. I need some chloroform and propionic acid, and a convenient way to make both is the haloform reaction. So let's get started. Get about a liter of sodium hypochlorite bleach that's been previously cooled in a freezer. Now this reaction is also quite exothermic, so it helps to build an ice bath around your bleach as well. Now I'm lowering in a thermometer to monitor the reaction. Now we start adding inorganic ketone. Most amateurs that do this reaction use acetone, but I'm going to use methyl ethyl ketone, also known as 2-butanone. Now the bleach I bought claims to be 8.25% sodium hypochlorite by mass, but I only found about 7% through titration. So I'm going to add a total of 22 grams of methyl ethyl ketone. Now there is an induction period between adding the ketone and when the temperature spike occurs, so don't add it all at once thinking nothing is happening, as reaction will boil out of control when it finally does start up. But don't take too long either, as the chloroform produced decomposes under strongly alkaline conditions. What's happening is a well-known reaction called the haloform reaction. In this reaction, 3 moles of sodium hypochlorite react with 1 mole of a methyl ketone to form a carboxylic acid and chloroform, as well as sodium hydroxide. Now the carboxylic acid is whatever was on the other end of the methyl ketone. So if acetone is used, then we get acetic acid. If methyl ethyl ketone is used, then we get propionic acid. So by using methyl ethyl ketone, we can create 2 useful products with 1 reaction. Try to keep the temperature below 30 Celsius and add everything within 30 minutes. Looks like I overshot mine, but it will still work. When the reaction finally finishes, the solution will go colorless as the yellow-green hypochlorite ion is completely consumed. Now the cloudiness is from tiny little droplets of suspended chloroform, so let the containers sit until they all settle out. Now chloroform is denser than water and will form a layer on the bottom. When it's fully settled, decant off most of the upper aqueous layer. You can now clearly see the chloroform layer on the bottom. Now I'm separating off the chloroform by withdrawing it with a pipette. And there we have our crude chloroform. I got about 17 grams for a yield of about 45%. Now the chloroform contains small amounts of water and unreacted ketones, so you can remove the water by shaking it with a desiccant, like anhydrous sodium sulfate, molecular sieves, or even sodium chloride salt. To remove the ketone and other impurities, you can fractionally distill your chloroform at 61 degrees Celsius. Celsius. Now, over time, chloroform slowly reacts with air and light to produce highly toxic phosgene gas. You can stabilize it by adding some alcohol like methanol or ethanol, around 1% by mass. It's also a good idea to store the chloroform in a dark or opaque bottle. Now, if you have chloroform that you don't want to deal with anymore and you want to get rid of it, you can destroy it by mixing it with concentrated sodium hydroxide and letting it sit for a few days. Sodium hydroxide reacts with chloroform to create sodium formate, which is benign, and salt. A lot of halogenated compounds can actually be destroyed this way. So here is the aqueous solution of the various products from the reaction of a full 1 gallon bottle of 8% sodium hypochlorite bleach and 93 milliliters of methyl ethyl ketone. The yellow color is from the various reaction side products, as I used excess methyl ethyl ketone rather than perfectly titrate the bleach to determine how much I needed. Now, the haloform reaction creates an alkaline solution, so the propionic acid is actually in the form of sodium propionate. We'll need to convert to the acid form to recover it. Now, to convert the sodium propionate into propionic acid, we add 600 milliliters of 31% hydrochloric acid. This is a huge excess of hydrochloric acid and will ensure the reactions proceed forward. What the gases consist of is small amounts of toxic chlorine from unreacted bleach and chlorine dioxide. This comes from the reaction of sodium chlorate with hydrochloric acid. Now, you're probably wondering where that sodium chlorate came from. Well, one decay pathway is the creation of oxygen, but another pathway is the creation of sodium chlorate. Decayed bleach contains small amounts of it that is now reacting with the hydrochloric acid. Anyway, I left this going overnight to remove as much of the chlorine and chlorine dioxide as possible. Now, to recover the propionic acid from the salt water, we use fractional distillation. Pure propionic acid has a boiling point of 141 degrees Celsius. Unfortunately, propionic acid forms an azeotrope with water consisting of 17% propionic acid by mass at 99.96 degrees Celsius. We're just going to collect everything at 100 degrees Celsius. A lot of that should be the propionic acid azeotrope. You're probably wondering what that white powder in the receiver is. That's sodium bicarbonate. As the distillation starts, what comes off first is the dissolved chlorine and chlorine dioxide. The alkaline sodium bicarbonate helps to absorb the gases so there is less emitted into my gas scrubbers and ultimately into my fume hood. Now, once the chlorine and chlorine dioxide gases are boiled out, some of the leftover organic chemicals will start distilling. This includes unreacted methyl ethyl ketone as well as unrecovered chloroform. So discard the first 1% of the solution volume, which contains most of the volatile organics. Now, I'm distilling 500 milliliters at a time since my apparatus can only handle that much, so I'm going to discard the first 5 milliliters of liquid in this run. Once that is distilled over, we now change out the receiver and collect our mixture of propionic acid and water. Now, a lot of liquid will distill over, more than half the original volume, so be patient. Propionic acid can also be recovered by liquid-liquid extraction using a non-aqueous organic solvent like diethyl ether. Since we use an excess of hydrochloric acid, it will start distilling after we've exhausted most of the water. When the temperature of the distillate starts rising beyond 100 degrees, we are beginning our transition. I stopped my distillations at around 103 degrees. So here we are with over 2 liters of distillate containing water and propionic acid, as well as around 2 liters of residue that contains mostly hydrochloric acid, less volatile organics, and salt. Anyway, we now have to separate the water from the propionic acid. We can't just distill it since it forms an azeotrope, so we're going to go a roundabout way and add sodium bicarbonate to react with the propionic acid and convert it back into sodium propionate. Since we don't know exactly how much there is, we'll have to crudely titrate by adding small amounts of sodium bicarbonate and stopping it when it no longer fizzes. At this point, all the acids have reacted. Now we remove the water by simply boiling it off. The color of the solution is from lingering organics darkening due to the alkaline conditions and high temperatures. Once all the water is gone, you'll have a mass of sodium propionate. Get its weight so we know how much sulfuric acid to add later. I previously weighed the flask and stir bar to 333.1 grams, so our sodium propionate mass is 58 grams. Now we liberate our propionic acid by adding concentrated 98% sulfuric acid, about 1 milliliter for every gram. You can already see the fumes of propionic acid forming. Some of these fumes are also from hydrogen chloride, as inevitably there was some sodium chloride in the dry sodium propionate from small amounts of hydrochloric acid that was distilled over. As usual, this must be done outside or in a fume hood. Now to distill off the propionic acid. Oh, looks like I blundered here and didn't adequately mix the sodium propionate and sulfuric acid beforehand. To solve this, I just added a lot more sulfuric acid to ensure everything is dissolved. Once distillation is finished, we now have a crude sample of propionic acid. And now we cannot dry it using molecular sieves since those decompose in acids like this. So instead, we dry it with anhydrous sodium sulfate and then fractionally distill it. Now we get our proper boiling point of around 141 degrees, and there is our purified propionic acid. My final purified yield was 42 grams, or about 44% based on methyl ethyl ketone added. We're going to make ethyl propionate ester by the classic process of Fischer esterification between ethanol and propionic acid. First, we start with an Erlenmeyer flask and add in 20 milliliters of propionic acid. Then we add to that 50 milliliters of dry ethanol. Finally, we need an acid catalyst, and we'll use 1 milliliter of concentrated sulfuric acid. Now we set up a reflux apparatus on top of the flask. Gently start refluxing the mixture. What's happening is we're reacting the propionic acid with ethanol to form ethyl propionate and water. The sulfuric acid acts as a catalyst. I refluxed for 3 hours, but this might be excessive. Anyway, here we are after 3 hours of refluxing and the flask is cooled. I've also removed the reflux condenser. Now we add 140 milliliters of cold water. The propionic acid, sulfuric acid, and ethanol are all very soluble in water, but the ethyl propionate has very low solubility and conveniently has a lower density than water, so it floats on the aqueous layer like an oil. We can then use a separatory funnel to separate just the ethyl propionate layer. And here it is, our sample of ethyl propionate. The mass is about 11.1 grams, so my raw yield was about 40%. The reason why the yield was so low was because the reaction is reversible. The water can react with the ethyl propionate and produce propionic acid and ethanol again. If we could remove the water, we could drive the reaction forward. Unfortunately, we can't just distill the water out because the ethanol and ethyl propionate azeotropes have even lower boiling points. Now, in a previous video, I showed that we could use molecular sieves to dry alcohol, and some have asked if that could be used for Fischer esterification. Unfortunately, we can't add the molecular sieves directly because the acids in the reaction would destroy them. Luckily for us, there's a workaround. First, we start with an Erlenmeyer flask and add in 80 milliliters of propionic acid. Then we add to that 100 milliliters of ethanol. Normally, you would remove any dissolved water first, but in this case we don't have to, as we'll be removing the water during our reaction. Finally, we need an acid catalyst, and we'll use 4 milliliters of concentrated sulfuric acid. The process so far is just like regular Fischer esterification. Now for the important difference. Instead of a simple reflux apparatus, we set up a Soxhlet apparatus filled with molecular sieves 3A. Okay, once the apparatus is all assembled and the cooling water running, turn on the hot plate. Gradually raise the temperature until it starts to reflux and condense into the Soxhlet extractor. You don't need a very high turnover rate. Now, as said before, the reaction is reversible, so we can never get a good yield just at equilibrium. The Soxhlet extractor helps us get around this. By cycling the water, alcohols, and esters around the extractor, we can gradually remove all the water and only the water, without losing our alcohols or esters as we would if we just went with straight distillation. Now at this point you might be wondering what happens with the acids. Propionic acid and sulfuric acid are too polar and too high boiling, so they don't vaporize and condense into the Soxhlet apparatus. Thanks to the Soxhlet extractor, we can use them for the reaction without actually using them in the reaction. In a way, we've built a mini chemical plant where we have two separate processes running, Fischer esterification here and water removal over here. Anyway, I'll let this run overnight. Okay, here we are the next day, and I've already turned off the heating. Once it's cooled, we pour 100 milliliters of cold water into the Soxhlet extractor. The water will now dissolve most of the components in our reaction mixture, except for ethyl propionate, which has very low solubility in water. The ethyl propionate will then float on top like an oil, allowing for convenient separation. To do this, we use a separatory funnel. You can see the layer of ethyl propionate floating on top of the water. Drain away the water first, and then collect the ethyl propionate. Now you might be wondering why I'm washing with water when I said water destroys ethyl propionate. While the mixture is cold, the reaction of water and ethyl propionate is very slow. And there it is, crude ethyl propionate. The mass of this is 103 grams for a crude yield of 93%. To improve purity somewhat, I'm going to wash it again with 100 milliliters of cold water. And there we go. This is 90 grams or about 81% yield. We're still ahead of the original method. Now I'm going to store my crude ethyl propionate over molecular sieves to remove the water. In my future experiments, I'll need it water-free. For further purification, we can dry it over some sodium sulfate and then fractionally distill, finally drying over molecular sieves. Now esters are known for their smells, and this ethyl propionate is no exception. It has a rather sweet, fruity smell. So that is how you use a Soxhlet extractor and molecular sieves to drive forward the Fischer esterification of ethanol and propionic acid. we're going to make 2-Para-Chlorophenyl 3-oxopentane nitrile. First, we start with 300 milliliters of methanol dried and distilled from molecular sieves 3A as I've shown in a previous video. Set up on top a reflux condenser. Now get 15 grams of sodium metal. Cut and roll the sodium into wires like this so we can drop them to the condenser. Now one by one, drop them in with the cooling water turned on. Don't drop in too much at once or the bubbling will go out of control. What we're doing is reacting sodium with methanol to make sodium methoxide while generating hydrogen gas. Considering that methanol and hydrogen gas are both highly flammable, this can go very bad very quickly. Eventually, all the sodium will react and we'll have a solution of sodium methoxide and methanol. Now reassemble your reflux apparatus into a distillation apparatus and distill off the methanol. We want relatively solvent-free sodium methoxide for the next step. Now turn off the heating, stopper the flask, and let it cool. While it's cooling, we can prepare our reagents. Get 30 grams of para-chlorophenyl acetonitrile, then add in 30 milliliters of ethyl propionate. Shake it up until everything is dissolved. Now with the cooled sodium methoxide, add the reagents. Now add enough dioxane so the total volume is about 300 milliliters. Now assemble a reflux condenser onto the flask again and gently heat until it starts refluxing. What we're doing is using the sodium methoxide to deprotonate the para-chlorophenyl acetonitrile and then react that with ethyl propionate to make 2-Para-Chlorophenyl 3-oxopentane nitrile. Looking back, I forgot to break up the cake of sodium methoxide first, but eventually with enough stirring, it'll break up on its own. Now as it runs, it may foam up. Adjust heating and stirring to keep foaming under control, but try to keep it as hot as possible. Anyway, keep heating for 2 to 3 hours. Then turn off the heating and let it cool. Now for the aqueous workup and washing, get a total of 1 liter of water and fill the reaction flask as much as you can. Mix it up with a glass stir rod and pour it out. Wash out the reaction mixture this way. I didn't just pour it out first because I found the mixture solidifies when cooled. Adding water first helps make it easier to work with. Once it's all in the beaker along with 1 liter of water, stir it for 10 minutes or so to thoroughly suspend the chemicals. Now add in 100 milliliters of 30% or 10 molar hydrochloric acid and keep stirring for another 10 minutes. Turn off the stirring and let it settle. What we're doing is neutralizing the sodium methoxide to sodium chloride and methanol. The sodium chloride and methanol are very soluble in water and stay in solution while the organic products will precipitate out. Most of this is done in a few hours, but I'm going to let it go overnight. And here we are the next day. The organic layer on the bottom should have our product. Now pour off most of the water and use a separatory funnel to get the rest. I recommend washing the organic layer again with 100 milliliters or so of water for further purification. And here is our crude 2-Para-Chlorophenyl 3-oxopentane nitrile. I sent a sample off for NMR analysis and got back this spectrum. Over here are the symmetrical aromatic peaks. This peak over here is the Chloroform D solvent peak since I asked the NMR lab to use Chloroform D for the scan. This here is that one little proton on the trisubstituted carbon. This spike over here is leftover dioxane. It wasn't entirely washed out with water, but it's not going to affect our future chemistry, so it's not worth putting an additional effort to remove it. Now for the interesting part, this complex multiplet is the protons right beside the ketone, and this triplet is the protons at the end. This complex multiplet is characteristic of our target compound, and this is very strong evidence we were successful in making it. Now this broad peak over here is water. For obvious reasons, we have a lot of water contamination. Overall, this spectrum pretty much confirms that we have our desired product. Our yield is 41 grams or 99%. We're going to make Trimethyl Orthoformate. Now it's a rather unusual organic reagent, so first a bit of background. The classic carboxylic acid group has carbon to which there is a double bonded oxygen and a single bond hydroxyl group. Now in theory, if you could react this with water, you would get a carbon bonded with 3 hydroxyl groups. This would be called a carboxylic orthoacid. Now as far as I know, these have never actually been made or detected, and even if they could be made, they would be incredibly unstable and quickly decay back into carboxylic acid and water. Now we know that if we condense the hydroxyl group of a normal carboxylic acid with an alcohol, we get an ester. This is well known in chemistry and done every day. If we went a step further and did this to our hypothetical orthoacid on every hydroxyl group, we would get orthoester. Interestingly enough, this stuff can be made using a roundabout procedure, and we're going to do just that in this video. We're going to focus on making trimethyl orthoformate. To start, get 200 milliliters of methanol and add 40 grams of sodium hydroxide. Then we start until completely dissolved. What we're trying to do is make sodium methoxide, but this reaction doesn't go to completion since it's easily reversible as the water reacts with the sodium methoxide again. To force the equilibrium to the right, we add 100 grams of molecular sieves 3A. Now seal up the flask to prevent the evaporation of the methanol, but more importantly to prevent moisture getting in. Now mark off the starting level of the flask and let it sit for a few days. By pulling the water out of the system, we force the equilibrium toward the formation of sodium methoxide. As this happens, the liquid level will go down as the water is removed. Now when the liquid level stops decreasing over a 24-hour period, we're ready to use a solution of water-free sodium methoxide and methanol. Now set up a flask and stir bar with a vertical condenser column for reflux. I should emphasize at this point all subsequent apparatus should be meticulously dried before use. This is because orthoesters are very water-sensitive chemicals and irreversibly react with water to release their alcohols and normal esters they are made from. Now transfer the sodium methoxide solution to the reflux flask. Try not to transfer any of the molecular sieves, but a few pellets is not a problem. Now turn on the cooling water and start heating the mixture until it starts to reflux. When it starts refluxing, turn off the heating and get 30 milliliters of chloroform. Now add the chloroform 1 milliliter at a time through the top of the condenser to the hot sodium methoxide solution. Do not add it all at once or the reaction will go into thermal runaway. Add in at a rate to maintain constant reflux. The reaction is very exothermic and will boil quite vigorously with every addition. What's happening is the chloroform is reacting with sodium methoxide to produce Trimethyl Orthoformate and sodium chloride salt. The sodium chloride has low solubility in methanol and precipitates out as a white powder that you can see here. Now even though the reaction is very exothermic, we start with hot sodium methoxide solution because the reaction proceeds very slowly at cold temperatures. The false sense that the reaction is under control can lead you to add more chloroform than the apparatus can handle, and when it does start up, the self-heating leads to thermal runaway. I'll admit I made this exact blunder and spent my Christmas cleaning my fume hood of the resulting chemical waste. Anyway, once all the chloroform has been added and the refluxing has stopped, turn the heating back on and reflux the mixture for 1 more hour. This is to ensure the reaction is finished. Then let it cool to room temperature. Now we need to remove the salt, so to do that we vacuum filter over a fitted funnel. Don't take too long though, as the Trimethyl Orthoformate is being destroyed by the moisture in the air. Here is our filtrate, around 150 milliliters worth. To recover the small quantity of Trimethyl Orthoformate, we use fractional distillation. What boils off first under 60 Celsius is an azeotrope of methanol and excess chloroform. This azeotrope has a boiling point of around 53 degrees Celsius. Then we boil off the next 100 milliliters of methanol at around 64.7 degrees Celsius. Trimethyl orthoformate boils at around 101 degrees Celsius, so when the vapor rises above 75 degrees Celsius, change out the receiver and start collecting the product. And there it is, trimethyl orthoformate. I only managed to get 7 grams of an expected 35 grams for a yield of 20%. Remember to add the chloroform slowly so it doesn't go into a thermal runaway like my not so successful attempts. I need a source of guanidine for my series on making pyrimethamine. It's actually a component of hair relaxants. Most products use sodium hydroxide as a base, but consumers have asked for alternatives, so this no-lye version uses guanidine instead as a strong base. To be sure, check on the ingredients list, and somewhere one of the components should be guanidine, usually in the form of guanidine carbonate. Now this also has plenty of other ingredients like dyes, surfactants, perfumes, and other oils, so we're going to have to run a few purification steps to get our guanidine. There is actually a lot of extra products like activators, shampoos, and washes, but we just want the component that has our guanidine. And here it is, the liquid activator as it's called. Pour all of the liquid activator into a beaker. The guanidine is all dissolved in solution, so to precipitate it out, we add 6 times its volume of acetone. As we add it with stirring, the guanidine carbonate precipitates out as insoluble in acetone. Now we simply vacuum filter our guanidine carbonate. Be sure to wash out the guanidine carbonate with some more acetone to remove as much of the additives as possible. And that's it, guanidine carbonate. Change out the filtering flask since we're going to be collecting our guanidine in it. Now to the guanidine carbonate on the filter, add hydrochloric acid until it dissolves. I used about 50 milliliters of 3% concentration, although looking back, this was probably far too much. This converts the guanidine carbonate into guanidine hydrochloride, which is highly soluble. Anyway, once everything is dissolved, turn on the vacuum and filter the solution through. Now we have our solution of guanidinium chloride. I want to precipitate it back out with more acetone, but it turns out it's extremely soluble even in a mixture of acetone water. Nonetheless, the acetone does help us remove more of the additives because some of them will congeal into some type of slime as seen here. So we filter it back out again to get our purified solution. Now we vacuum distill the solution to get dry guanidinium chloride. And there it is, guanidinium chloride. The total mass is 15 grams. We're going to make 2 para-chlorophenyl 3-methoxypentuenenitrile, but I'm just going to call it the eno ether to save time. We take our entire 41 gram stock of 2 para-chlorophenyl 3-oxopentanenitrile and place it in a flask. Then we add in 50 milliliters of toluene solvent. Be sure to add in a stir bar. We set up on top a Dean-Stark apparatus and reflux condenser. Turning on the heating, we raise the temperature until the mixture starts to reflux. What we're doing is removing the water in the mixture by distillation. Water forms an azeotrope with toluene, and the Dean-Stark apparatus lets us separate the toluene from the water and return the toluene to the mixture, continuing the cycle. Now remove the Dean-Stark apparatus and assemble back on the reflux condenser. Through the top of the condenser, we add in 30 milliliters of Trimethyl Orthoformate. Then we add in 75 milliliters of methanol that was dried over molecular sieves. Finally, we add in 0.5 milliliters of concentrated sulfuric acid that I distilled from drain cleaner. Now heat the mixture until it refluxes. What's happening is the Trimethyl Orthoformate is reacting with the oxopentanenitrile to form an eno ether. Interestingly enough, if you watch closely, you'll see the liquid level decreasing despite efficient refluxing. What's happening is we're losing methylformate as it boils out. Methylformate has a boiling point of just 32 degrees Celsius, which is too low for my reflux condenser to efficiently condense. So it boils out and is lost in my fume hood. Anyway, swap out the flask of eno ether mixture and put the reflux condenser on another larger flask containing 200 milliliters of methanol dried with molecular sieves and then distilled. Now get 15 grams of sodium metal that we made and rolled into wires. Add them through the top of the reflux condenser a little at a time and keep the reflux under control. What we're making is sodium methoxide and methanol solution. Once it's all added and cooled, take off the reflux condenser. Now add in 20 grams of guanidinium chloride. We're reacting the sodium methoxide with guanidinium chloride to make guanidine and sodium chloride. Anyway, now that we have produced guanidine in solution, we have now cleared the last precursor step. Only step 7 remains. To do it, we add in the entirety of our eno ether reaction mixture. The excess sodium methoxide will react with the sulfuric acid and turn it into sodium sulfate. The excess beyond that will flip the acidic conditions of the eno ether formation to the strongly alkaline conditions we need for the guanidine reaction. Now put the reflux condenser back on and start refluxing the mixture. What we're doing here is reacting guanidine with the eno ether to form a pyrimidine ring. This is the final reaction in making pyrimethamine. The reaction is slow, so you'll need to reflux for a long time. I left this going for 36 hours. And here we are 36 hours later. Turn off the heating and let it cool. Now we need to start the complicated process of separating out the pyrimethamine. Take off the reflux condenser and assemble a distillation setup around the mixture. Now distill off about 100 milliliters of liquid or so. Now turn off the heating and add in 100 milliliters of water. Turn the heating back on and keep boiling off more solvent. I want to essentially remove as much of the organic solvent as I can and replace them with water. I didn't simply boil down dry earlier because I don't know how sensitive pyrimethamine is to heat. If I boil dry, I could destroy the pyrimethamine. Adding in water first means we can remove the solvents and still remain below the boiling point of water. Keep boiling until the distillate temperature goes past 90 Celsius. At this temperature, most of the methanol will have boiled off, and conveniently, toluene and dioxane will also boil off since they form azeotropes with water below this temperature. Now turn off the heating and let it cool. Now we add in 23 grams of sodium hydroxide and stir. I want to make the water even more polar so it will absorb all the highly polar impurities, but reject the non-polar impurities. Now place the mixture on ice bath and let cool. Once it's cold, we add in 150 milliliters of diethyl ether that I extracted from starter fluid. Add in another 200 milliliters of water and let it stir for about half an hour. Turn off the stirring and let it settle. And there we go, this is much better. We have a clean aqueous layer that dissolves all the salts and other polar side products and contaminants. And in the upper ether layer is where all the non-polar impurities collect. In the middle is a layer of pyrimethamine. It has only minor solubility in both, so it separates into its own layer. I first collected the middle pyrimethamine with a separatory funnel, but this is optional. Suction filter the mixture to get crude pyrimethamine. Wash it once with water and twice with ether to remove more of the impurities. Then let it dry on the filter. Scrape it off, and here is our crude yield of pyrimethamine at 5.5 grams. To purify it further, we crystallize from ethanol. Put it on gentle heating and add ethanol while boiling until it dissolves. I found I needed about 90 milliliters of ethanol to fully dissolve my pyrimethamine. Once it's all dissolved, turn off the heating and let it crystallize back out. Most of it will still be dissolved in the ethanol, but what we get will be exceptionally pure. And here we go. Now filter the crystals and wash them with some ethanol. Then wash them with diethyl ether. Now leave under the vacuum stream to dry. And there we have it, 2 years of work. Nonetheless, we finally have pyrimethamine. I sent off a sample for NMR spectroscopy analysis and got back this spectrum. These peaks here are the aromatic protons, and this peak here is the chloroform D solvent peak. This peak here is the amine on the guanidine structural element. This peak here is the amine on the hydrocarbon backbone. This peak here is the CH2 on the ethyl group, and that peak there is the CH3. This broad peak here is water contamination for obvious reasons. These very tiny peaks here and here are diethyl ether. This is leftover contamination from when I washed the final product with diethyl ether. This tiny little peak here is not supposed to be there. It's some sort of contaminant. It looks like acetone, but I can't be sure. It also doesn't make very much sense to be acetone since I never used acetone in the final steps. Nonetheless, we have made pyrimethamine, finally. We have now cleared step 7 and have confirmed our product. Time to break with the champagne. Our total yield was 1.8 grams. This is about 72 pills worth. Although most of it is still in the ethanol filtrate, and with further purification, I'm sure it could be recovered. You're probably asking what the overall cost and yield is right from the beginning. Unfortunately, because of the huge number of failures, repeats, and do-overs along the way, the numbers don't have any meaning anymore. The total cost spent to do all the research was about $22,000 over the course of 2 years. Keep in mind this is not the cost of the actual process. This is the total cost of all the work and huge amount of failure that went into researching, designing, experimenting, and verifying this pathway. The cost of chemicals, space rental, broken equipment, as well as my own time as a PhD chemist is also in there. Going on the raw cost, this batch right here is worth about $300 per pill. I know it's stupidly expensive, but that's to be expected for a first time laying out the pathway. But now that we have it, to repeat it would cost a tiny fraction of that amount. Anyone copying me would not have to go through all the failures I did. As a rough conservative estimate, I think this can be fully repeated with $1,000, for a projected cost of $15 a pill. And this pathway isn't even optimized yet. There are a huge number of improvements available at each step, as it just eyeballed the procedure for the most part. Now that we have a starting point, I'm sure that with some refinements we can get much better yield than 1.8 grams for an even better cost ratio. For example, just getting the full 5 grams from the ethanol solution would get us to $5 a pill. Optimizing to less than $1 a pill should be very straightforward. But I never meant for this to be a viable option. Even if this could be made completely free, the process is far too complicated for anyone to perform. If you actually need it, you have far more pressing concerns on your mind about your health than how to manufacture a drug at home. Additionally, this is not medical grade. To get medical grade certification, I need a huge amount of purification and testing every step of the way to ensure absolute purity and quality. I don't think reactions performed in a soup can would pass any sort of medical certification. Finally, for all the work we've put into this, it probably would have been cheaper just to go through the whole licensing and business startup procedure and order all the direct precursors. You can make kilograms for pennies. Making it from domestically available chemicals makes about as much sense as building a computer from sand. It can be done, but you don't really need to. This was more of a challenge, like climbing Mount Everest. Nonetheless, I've proven you can make anything from anything else, as long as you have the right elements, knowledge, and work. At this point, I'd like to thank you, my viewers, for pushing me through this when I myself had my doubts and was ready to give up. I'd also like to extend a special thanks to my Patreon contributors, both past and present. I wish I had all your names here, but Patreon doesn't list former contributors. Nonetheless, if you contribute at any point, then this thanks goes to you. You know who you are. There is no way I would have been able to fund a $22,000 amateur research project. It was because of you that this happened. This channel honestly would have died 2 years ago if it wasn't for you. Thank you. At this point, I'd like to extend an invitation to anyone who wishes to be a contributor. A project like this is dependent on outside support, and I hope I've proven that I can get them done. But for now, let's just appreciate a goal accomplished with plenty of trials and failures, as well as great and successful detours and stops along the way. If there was ever time to break out the champagne, it's now. Thanks for watching.